Okay. Hi everyone. So today is chapter 8. I can see apologize because I see today many typo. There are also some typo on my slides and on the website. So I will correct this soon. So today we will move to just for 2 lectures, just to have a little bit some overview about sequence model and mainly to recurrent neural network. So today the goal is to go through the sequence data, some an overview of some kind of application, and I will introduce the recurrent neural network. I hope to have the time to explain what is the back propagation through the time. And tomorrow we go to the long short-term memory, LSTM, which is an improvement for the RNN, and give some introduction to transformer and some autoencoder for language translation if we have time. So, okay, put the chat here. 23 people. Okay. I want some interaction today, yeah? Looking forward to transformer. Oh my god. It put some pressure on you. Okay. So, no. Where is my slide? Is here? Yes. Okay. So for introduction to sequence model, so we use sequence model when we analyze sequential data. So like text sentences, time series, which is quite the main application, straightforward application, or over discrete sequence data. I think I have an application with discrete data like the DNA, which is there are some sequence of the DNA. So we have seen that the convolutional neural network is used to have a specific for spatial information. But today we will use some kind of neural network for sequential information. So the key point is that the data that we process are not independently, are not high ID. Why are not high ID? Because as we have some sequence of data, we have some dependency in the data due to the sequential order of the data. So these sequence models are very popular in plenty of area like a speech recognition, voice recognition, time series, and also is a big area is natural language processing. So we just give some example, and you can I can give you some nice course which is in Stanford, which is like a full unit on natural language processing. So 40 hours on natural language processing and more. Okay. So yeah, I just list some application, and we will go through some application which could be also useful for you to choose to give some idea for your project. So for example, an application which combine in fact CNN and sequence model is image captioning. So is to put a caption of an image by analyzing the image. So I just put these figures where you have a giraffe and you use first a CNN, which after the output of the CNN go through LSTM, which is a kind of sequence model, and you have the caption of your image. And so if you click on the C data is there, I will click on this. You tell me if you see this. So this is a nice paper, and it was in 2019. And in this paper, we present different way to do some this task of image captioning. So it's quite, so this is my giraffe, and this is some chess player, and you have kind of different possible caption of each image. And you have also some different way to do this. And so we present a CNN combined with a long short-term memory, we'll see tomorrow, but you do also via CNN and CNN. And we also use some generative adversarial network, GAN, so we have seen yesterday. So I think is a good paper to have a look on this application. And yes, I want to tell you this. What I wanted to show, so I think on this paper, no, that's not a nice paper. Okay, so back to the slide. So second application in the time series. So time series, and so this example is stock market prediction, and you can use a neural network, a recurrent neural network, to do some prediction of the stock market prediction. And so if you click on this paper also, which is also quite a recent paper, which published in PLOS ONE, and in this paper, I wanted to show you this because he used also a long short-term memory to do some nice prediction, but also he will use some stacked autoencoder. So autoencoder, I will just take some few minutes to explain what is autoencoder. Can you tell me if Yoni, I think Yoni explain a little bit, yeah, with the GAN or the autoencoders? Is it? I don't think so. Okay, so I will go back to the autoencoder. So this is also could be a nice paper for your project, for if you want to do some prediction on time series. So where is my come back? Prepare. Ah, okay. So I leave some place here. So the if I leave some place, it's because I wanted to write something about the explain latent space. Okay, so the autoencoder is in fact is in unsupervised framework. So you don't have an outcome, and the idea is to learn representation. So it's like an encoding. Is to learn a representation of your data. Learn a representation. And I will say is also like a dimension reduction tools. So if I do, you can see some picture like this. So you have your input. I put this here is your input. So you just on your data is input unsupervised. And so you will build a code which is doing by a hidden layer. So this is your code, which code your in fact your input. So I'll put H here, and it will produce same dimension. I'm very bad with the picture. Huh? And you have the X tilde, which X tilde is a representation of your input. So you hope that X tilde is close to X on your input. So this part is called the, I will put this like this, I don't know. This is the encoder. And this part is, you know this part, what is the name of this part? You know? Yes, of course. Thanks, Anne. She promised me that she will participate. So good point. Is a decoder. So you have your X, your input. You build, in fact, the idea of the encoder is to learn to copy its input to its output. Okay? And how to do this? So how to do this? Technically, very simple. You need to write a loss function. So between X and X tilde. I will not go in the details, just with the information. Yes, it's decoder. Yes, perfect. And so you will take the square loss. So X minus X tilde and then like this. But if you do this, You tell me, okay, but at might is depending of your layer, what you put in your code. But if you're doing this, you will have some trouble because you will be completely overfit, and in fact your x tilde will be exactly x. So you will not learn anything. So the idea, I put a nice picture here. So you have your input and your hidden layer, which is a bottleneck, and your output. So in fact, is the autoencoder, you need to do the balance between sensitive and insensitive. So sensitive to the input enough to have an accurate reconstruction, but insensitive enough to the input that the model doesn't simply memorize and overfit the training data. Okay? Because it's overfit, it will not gain anything. So how to get this code is this loss function I told you, but do you have an idea how to do something with this loss function to not overfit? If somebody have an intuition about this? Realization, yes, very good. So what we had? So what I need to add on my optimization part? A penalty term, yes, thanks. Give me more, yes. So I will put a penalty term plus a penalty. You will be a parameter and I can do a penalty term. Okay? Penalty term on the weight in this part. Okay? So this is a key point. So you do a penalty part, and after there's also some different way of to do this. So this is an encoder decoder. Okay? So this is like you can see this like a dimensional addition. So the dimensional addition, maybe, I wanted to ask you the main point on the popular technique for the dimensional addition. And then a connection, also I want to show you a connection between autoencoder and a PCA. Do you know what is a PCA, everyone? PCA? Yes, so PCA stands for everyone know PCA. If some people doesn't know PCA, everyone know PCA. Perfect. So principal component analysis. So mainly you have a matrix like this, and this is your matrix X, and in fact you will have a shorter matrix. You will have some component, which each component are component 1, component 2 are linear combination of all your column of X, and based on your component you can reconstruct X. Yes, I have the same dimension. Yes, it's a copy of X. Very good, then. Exactly. So maybe it was this and not the code are not the same dimension, because if you put the same dimension, you will overfit. So this is smaller, but this is completely the same dimension. Okay? You try to reconstruct your X from the start. Okay? You have your X, you do a code, and after you can use the code to produce your X. Okay? Good? Okay. So PCA is another way to go from, in fact, PCA you can go to X and to go to an X tilde, but in a kind of different way that the autoencoder works. And the PCA, you can do a PCA with SVD. So the SVD is a very nice tool. It's math, and I know that everyone knows what is a SVD. So the SVD is singular value decomposition, and the SVD is for any matrix of rank R, any matrix of rank R, any dimension. I say matrix of P rows, Q columns of rank R can be decomposed as a product of three matrices, U, delta, and V. And the product is U delta multiplied by V transpose. And in U is two orthogonal matrices which contain the normalized left singular vectors and the normalized right singular vector. Everybody is familiar with this? Yes, okay, perfect. So this nice truth is that with M, if I do the decomposition of with the SVD, with these three matrices, and you can see that M is reconstructed by this sum. And you sum until the R the rank. Because in fact, if you will have this matrix, delta, will have some singular value equal to 0. So in fact, this stands at equality. There's not any approximation, it's an equality. So this is very important. And why is useful this SVD is from, you might know because you have done math, this theorem from Edgar Jung in 1936. He says that the truncated SVD for a given matrix M of rank R provides the best reconstruction, so is closest in kind of distance. So the distance is the least square of M by a matrix of low rank R. So it's the meaning that if I'm looking for the matrix R of rank K lower than R, is defined by the this is my matrix A, which is the closest to M, and how is built this matrix A is using the left and the right singular values, the first K singular left and right singular vectors, and to reconstruct M. Make sense? So in fact, is the meaning that when I have my decomposition of U delta V transposed, if to U I take just the first, I have this U is like this, and in fact I don't take this one, delta, and delta here, which is diagonal, and I don't take this part, cut, and I have V, I don't take the first part, the last part. And if I use this, I will end up that A, which is quite close to M. Makes sense? You see the point? Clear? Clear? I keep going. No question? Okay, and why is useful this? Or you that minus be open if you are not the same shape. Minus sign. Where is the minus sign? I don't get your minus size. Is all the same size because look, M is, I don't get it. Ah, okay, M is P. So it's the same size. You look at the 4, it's not the same rank, but you're looking at a matrix of size P by Q. So any matrix of size P by Q of lower rank. I reply to your question, Jade. Okay, and this sum, because each element, this delta L, UL multiplied by VL transpose, give a matrix of size P by Q. Okay, and you sum and you add more information. Okay, and so, okay, here I just copy, put the R code for people are fancy of R code, but the people who don't like R, no worries. It's just to tell you that I took an image. You will see the image after. So it's in image in RGB. And so in image in RGB, you know that now you're familiar with the RGB. You have these three matrices, so it gives you an array, and you have this tensor, and you have these three matrices, R, G, and B. And I have done, here you can see the code, just to explain what I've done. I did a SVD on each matrix, from the R, the G, and the B. You tell me when it's not clear, you stop me, okay? So I did these two, this SVD. So the SVD is a full decomposition. Huh? So if I take all the components, I have the same thing. So what I want to do is to do some dimension reduction approach, some compression. So I just create a plot function, and in my code here, I just did the compressed image, but just to don't worry about the code, just to tell you that on this code, you're familiar, is a similar code everywhere. In this code is meaning that I take just the first, not all the component, but the first nb.comp component. So from U, the matrix U, which is like this, remember the matrix, and the matrix V is like this, I just take the first component. So I take just this part. And on V, I take just this part. Okay? On each submatrix. And on this, after, I reconstruct my matrix. So at the beginning, I have a matrix for R, I have a matrix for G, and I have a matrix for B. I'm doing a SVD on each matrices, and I take just the information of some of the first component. And I reconstruct my R, so I put R tilde, G tilde, and B tilde. And after, I will produce the image. So what I have done this. Oh, who is this guy? You know who is this guy? So this guy is, in fact, is me when I was young. President of France, soon, okay. It is me when I was young. This is the original image, okay? And now this image is a reconstruction of this image. It's like I'm doing, in fact, you can see that I could have done this with an autoencoder, but I did a SVD. So here it's just based on 20 components. So 20 components, you understand what I have done. I have just done take the first 20 column from my SVD. And after I will multiply from the theorem of Encoder and Young and manage to get it. All good? So what happened if I took less component? I should have done this. Less component, clearer? You think my image will be better if I take less component? Yes. Thanks. I like this, Matthew. Yes. Less component, less Benoit. It's true. So, and if I put more component, I take all the information, and at the end of the theorem, I will have exactly the same image. Okay? Yes. Thanks, Jade. Right, get it. And so why we do this? Okay, and just show you that in the maximum of my image, it will be 170. I just take 20, and with 20, we can have enough information to recognize me. So the first took this, the original image, in terms of byte on the computer of memory, but in the compress is this. So we earn a lot. Okay? Okay, now SVD is very popular, and you can see that the SVD also, it could be used, or the Pca SVD, similar, there's some relation to do it. And you can see also when we talk about data augmentation, remember, you need always a lot of data, especially when you work with image. But to do data augmentation, in fact, you can do this. People do this also, do some Pca. In fact, you have your original image, and you more blurry, and you have a new image. Make sense? So it's also useful for data augmentation. So what is the relation with autoencoder and Pca? In fact, if I click on this link, I think I took this picture on this link. I click on this link. Which is a nice paper, 2019, and he explained that if you do a linear encoder, autoencoder, is the meaning that you just put one hidden layer. So you have your input, autoencoder, your hidden layer, you just put one hidden layer, and the output. If you take one hidden layer and if you use a linear activation function, in fact, you end up by doing to be in the same direction of your PCA. So this is explained in this paper. So it's quite nice too. So he explained this and the relation to by doing. I come back on. I prefer to. Sometimes I think I'm not so clear, but if I'm doing autoencoder like this, and I put just a smaller one, just one hidden layer, and in the activation function, what I use here is activation function is an identity. So if I use sigma x, it's equal to x. In fact, the relation of what I'm doing is the same as the PCA. But the advantage of the autoencoder is, I hope it's clear you have some data with just two features, x1 and x2, you have some data. And what is the PCA? The PCA is try to find a new component, which is a linear combination of your features. So you have just x1 and x2. So in the PCA, when you have just two dimensions, a linear combination, it will be a linear combination of x1 and x2. So in this case, it's just a line. So, and how to get the first component in the PCA, you try to find a line which maximizes the variance in projection. So you want that if you do the projection of each data on this line, and you take the variance in the new lower dimensional space on the line, you get the PCA. Okay, the direction. But I will just want to tell you that if you do an autoencoder and if you don't put an activation function like sigma x, but you put a sigmoid, for example, something non-linear, sigmoid, you will end up with something non-linear. Okay? That's the idea of the autoencoder. Was clear enough. So the autoencoder, we didn't go to the recurrent network, but step by step. Okay, if it's clear enough, we keep going. Just want to know 24 people. God, not enough. Okay, so I was still doing some application. So the sequence model are very useful and exploited in natural language processing. And one of some tasks, many different tasks, but the main one in the machine translation, but is also text mining and sentiment. So I put, I think, learning word vector from sentiment analysis. I think I have also a paper which here. So just some idea of a nice paper for learning word vector for sentiment analysis. Also in NLP, I hope you can see it. This one, I'm not so sure if it's available. Okay, just give you. And in machine translation, which is like a huge field. So you know it is a machine translation. Given the input on language, you sequence model to translate into different languages. So I put something in French. In French. Input, je suis étudiant. Encoder, decoder, I am a student. And this is by doing a sequence of data because we are a sequence here. So we do some recurrent neural network. Okay? Okay. different application here. I will not click on all, but there are some quite very nice. So you can click on the link, and as is 5:30 and you want some music, you can see this nice application, which is RNN, a recurrent network, to produce some Eminem sound. I don't know if you get it. You have the sound or not? You get my sound or not really?
I'm not a gold gets rape of M for this right now.
Ah,
And
it's low.
cheating we love what? I'm starting a roof on fire, you feel every time I'm sliced it in for the shit. I'm fired to get it the started things that got.
Okay.
You're dealing to my balls.
So it's quite good. Ah. No, 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 this is not good. Okay, back. But if you prefer some music, classical music, this is a very nice post and tutorial on how to compose music with recurrent network. Jade is a good question. Recurrent network can work with different lengths, and this is the power of the recurrent network. So, and in this application, he gives you some nice, I don't know if you can hear this. So this is producing by recurrent network. Okay. And stop. Okay. So there's some nice link, and the last one is a paper to generate classical music using a recurrent network. Okay, but now we need to go to the recurrent network. So the recurrent network, RNN, recurrent neural network, is specially designed for sequential data which are not high idea. And the good point was a question of Jade. They can tackle the following challenges. So you can deal with different variable length sequence, and you can maintain the order of the sequence, and you can track some long-term dependency. And we'll see a little bit that there's some improvement after. And the share parameter, this is an important point, we'll see across the sequence. Okay, so now an explanation of RNN. So we have seen until now some classical feed-forward neural network. You have the input, you have a hidden layer here, we call it hidden layer, and after the output. And so the recurrent neural network comes from the name recurrent because you have an edge there, which is a recurrent edge. And edge now is called a hidden state. And this hidden state, it will be at each time point, at each time t, and due to this recurrent. But it's easier to understand this picture if you unfold the representation. So this one, in fact, can be seen like you have xt, you have your hidden state, but to get some information from the past, you get information from the past from the hidden state from the time t-1, the time before. So this is a recurrence, and so on and so on. So after this hidden state is input for the next state, hidden state, which is all still the h, but at time t plus 1, and you have your input and you have the output. So the recurrence here, yes, the input are fed one at a time. So you arrive by the recurrence is the cell state ht. So it's, the script here is for the time is a function of the old state and the input vector at the time t. So one at a time. Okay? And the main point here is this W. The W is a weight, but F is a function parameterized by the weight W. And at every time step t, we have the same function, and we have the same set of weight. So this is the point. F, same FW, same set of weight. And it propagates like this, like a recurrence. Okay? But this is the first one, a simple one, but you can have a multi-layer RNN, of course, deeper and deeper. So same principle, but you have adding one layer. Okay? So this first part is the first hidden state at H1 and is going to the second hidden state to produce the output. And after, it goes through the time. Okay. So now we'll have more, maybe, yes, more details. So this is my recurrent neural network. We put some notation here because we have a goal to do the back propagation over time to know how it's working. And you can see this in neural language processing as an example. So imagine that your input data are the sequence input are in fact a sequence of m words. I have m words. So each x1, x2 is a word from your sentence. Okay? And this will be the input. It be the word. So each input is a word. Okay? But there are a flow of the word. Makes sense? So at each time t is a word, and this belongs to R V, and V is your size of your vocabulary, because you know that in a neural network you cannot feed, you need to feed some numerical value, so you need to code this word. And the way to code it in neural language processing is to use the one hot vector framework. So everybody is familiar to the one word vector. So for example, you have a vocabulary which, I don't know, 1,000 or 10,000 words. And if you have, for example, a cat, it will be coding that like, I don't know, 00001, because for one is cat here in your vocabulary. Make sense? Good? So in fact, you don't, they don't have any trouble about the repeated word. If you have a cat is biting another cat is not a problem. Cat is biting another cat, and you will be like this. No worries. I don't get the. You need to give me more about the sequence satisfies the Markov property. Yeah. But I will come back on this. So let me finish about the notation. So at this stage is the same. We talk about x. So h, we have also ht, this one. So this one, what is equal? It equal to a nonlinear function activation function, and you have okay ht. Can you help me? What is equal to ht? So this is my ident state. So we'll have okay w. So WHH is this one, is a weight matrix here. So WHH multiplied by what? I will say H, so the previous ident state, and plus, so HT there, this one here, is what? This one, this weight, multiplied by this one. And after you have the input at time t multiplied by this weight. So you multiply by W H X multiplied by X times the input at time t. Make sense? So this is my recurrence. Okay. Can you tell me what will be the dimension of the matrix WHX to see if you get it? What is the dimension of this matrix? And I would like to have, and I will say that first that DH is the number of neuron in each layer. Good point, very good point. This is very important. W, this shares the same because the recurrence. So this is the recurrence. This is the same WHX and it's the same WHH here and the same WYH. Very important. Okay, so this dimension of this matrix, I will tell you that is R because we have DH neuron is DH by the number of your vocabulary, the dimension of your vocabulary. Okay, and so and H T minus 1 is the dimension of R DN. Make sense? All of this? What we have? We have also YT. What is YT for you? What is YT for you? You lost? I think I lost people. Okay, it's not really, yes, okay, I cannot see. You can see like the output, in fact, is a desired output. It could be confusing, but we have this data. Is the next one, in fact. So very different. So this is a one hot vector of size also v, and in fact we have based on our notation is so good. We have also a y. I think Jade wanted to talk about this one with a hat. We have the one with the hat, which is a prediction. And we have also the one which is not the prediction, the observed one. Yep. Is clear, more clear? You see the difference of the y hat t and yt, or are those people? I don't see the importance of this. What is if you have another language, you will use another. It will be a problem for translation. We don't do translation at this stage. I haven't said what you have. But I think yes, in some recurrent network, we should have there's some trick to do when you do the machine translation. Okay, I wanted to precise this, but how to get the y? I just want to precise this. The y, how to get the y at t, the prediction, and generally because you will do the soft max of w y h multiply times h ht. Make sense, this one, my last one? So this part is to get something the prediction for this output. But this is the true one. The desire. Okay, oh, it's already 50. Okay, and just no question on this. We have different sequence. I will talk about the Markov after. I haven't forgot this. So there are different type of sequence modeling, and many. So there are different applications. So you have many to one to many, many to many, many to many. Oh yes. So this is using for doing the translation. I think yes. So this is kind of many to many is and this direction is when you do machine translation. You have je suis étudiant, and you come back at it's not exactly this. It will be a bit one more. So you have the many to one, which is some example is a sentiment classification. So in fact, you have some text here, sentiment classification, some text, and you want to know that is positive or negative, or something happy, sad. Okay, you get something. So what will be the air to get this one, to get this output, happy, not happy, or positive, or negative? What will be the activation function for this part? Question here, activation function of this part. Okay, I have one question after I reply to your question because time. Sigmoid, thanks. Okay, this is for the sigmoid. So, and some over will be different because one too many it will be different and so on and so on. Okay. So, what is how to train a recurrent network? It will be for tomorrow, and we will see also some mini improvement of the recurrent neural network. So, what is your question, Jade? Do you have any research you can recommend? I read about that. About that what? Because that there are a lot of things that. So Jade. At Matthew. Okay, Matthew. I even say what is say Matthew. Matthew. Jade, let's take the extreme case where you want to reverse the sequence. And you can pad the opposite so the end. Yeah. So the answer is that sentence is encoding in the hidden state. And now you start again. What? Okay. So I think I can give you some tomorrow. I will try to find some. There are a lot of sources. I try to find a good source if you're really interested by natural language processing Jade. Okay. And I want to come back on the Markov question, which has completely forgotten to reply. Why is it the Markov? And then maybe I didn't get it. Why is it the Markov? I don't see it. Who asked me a Markov problem? So hidden state can hang on multiple. No, it doesn't assume the yes. It takes all the information the past. So okay, let me think not to say a big mistake. Two new message. Yes, Markov property. I know what is a Markov property. Thanks for. Okay. Yes, this one is a good one. Also the course on Stanford. Okay, any questions? We are on time, not on time, but so it's time. Question. I have a question for you. Have you learned something today? I have a question. Have you learned something today? Yes. Now, well, second question. I'm happy of this. Very happy. What have you learned? Because this is my goal, that everyone learns something every day. Thanks a lot, Matthew. This is a good one. I like it. I hope you learn a little bit more, but it's okay. Thanks, Jade. Yes, this is the point. Okay, I have 22 participants. Before leaving, I want some 22 response. Weight stays the same. Yes, Spencer. Good. We do a summary. Yes. Okay. So people who have replied to learning, we can let. We can leave. No more? Nothing? Yes. Thanks, Matt. Good one. Okay, I think I have the name of the people. Is it? Not sure. Not so good. Okay. Yes. Yes. Linear autoencoder. Yes, true. Mathieu. Good one. Merci, Benoit. Okay. Time to go. Okay. We will ask Sarat to see if he was sleeping or not. Sarat, do you have learned something?
Yes, SVD.
What do you have learned?
SVD, singular value decomposition.
Yeah, good point.
No. A lot I learned.
SVD, image compression. Good. Thanks. Good. So tomorrow, I think Yoni he gave me an information. I think he put some reference on the GAN on the chapter for your final assignment for your project. So you are more references. I think on this chapter, he told me that he had something. So
you might receive the recording for this lecture. Can you send that recording to Yoni later?
I think he does. I don't need it because it's not mine. My spot.
No, I made you host. Probably you will receive the recording.
Okay.
Yeah, I'm not sure, but yeah.
Yeah, okay. Thanks, everyone. I hope to see you tomorrow. We still have 22 tomorrow. It's at 4 p.m. tomorrow.
Thank you, Benoit.
Have a good evening. See you tomorrow.